do a couple of examples from out of chapter 11, and I'm going to do some of the theory. I'm not expecting you to be able to calculate the test statistics by hand, but I'm going to show you where they come from. And I got some links to some applets, so hopefully that'll help you do this. So what we're going to look at is some more significance tests. The last two we'll look at this term, and I'm going to do these in a little bit reverse order from how the book presents them, because I think it's easier. To me, it makes sense this way. So a goodness of fit test, you're just dealing with one variable and a bunch of categories. For a test of independence, it's how do you see if there's an association between two categorical variables. What we've just spent chapter 10 doing is looking at how do you figure out if there's an association between two quantitative variables. We use R and R squared and residuals, the whole bit. Similar techniques, but it's not. And this works for the categorical variables, I guess. I said that once. So, goodness of fit test is one that asks me if a distribution follows what we expect it to be. And if we were in the classroom, I'd bought you some M&Ms, or this is M&Ms. So what we do is we'd break open some bags of M&Ms and do the counts, and then see if the counts there fit what the M&M Mars, Mars and Mars says they're supposed to be there. So here are, this came out of the textbook. I don't remember. I think it's question 5 out of 11.2. So one thing that's really important to remember is that you got to have counts to do this. And if we look at this, there certainly are some counts there. That's how many. They don't tell us how many case of candy. So they got this distribution, and this is what we observed. Now, Mars and Mars says that this is what they should be. 24% of the candy should be blue, 13% should be brown, 16% should be green, yada yada. Okay, and then they do the total. Now, in order to make this work, we get some assumptions and conditions to consider. So first off, we need to have counts. So you remember how if you look back at that last table, you see the expected values were not counts. Those are proportions. So we're going to have to do a little bit of calculations to make this work. So we've got to make sure we have counts for both the observed and for the expected. Are they independent? Does one color affect another? And is it a random sample? So those are all things that we have to worry about. The other condition we have to worry about is we need to have at least 5 in each cell. If you don't have 5 and you still want to do the test, you're going to have to combine some cells so you have at least 5. Otherwise, you aren't meeting the conditions you need for the test to work. And it's similar to that central limit theorem, though not. And this is kind of what this blurb is talking about. Okay? So the test statistic for these chi-square, for these goodness of fit tests, is called the chi-square. And it's written like a fancy X with a square. And if you ever were in a fraternity or sorority, you had to learn about chi. Or maybe you've seen it on something like Mean Girls or something like that. So the way you calculate it, you're going to do the observed value minus your expected value. So this is like a residual, like what we did with the quantitative variables, with the regression. We're going to square it just like we did with the residuals, but then we're going to divide it by the expected. That didn't have a relationship to the other calculation. But just so you know, it is similar. Even though we're dealing with categorical variables, we're testing for an association, so there's some overlap here. And we're going to walk through this again. I'm not going to make you do this by hand, but I want you to see where it comes from. So how do we deal with this problem? Well, remember we have to have counts. What we're going to have to do is we're going to have to multiply 0.20. So there's a total of 2620. We're going to have to multiply 0.24 times 2620 to get that value. So when I did that earlier here, I got 628.8. Then I'm going to multiply 0.13 times 2620. And again, when I did that earlier, I got 340.6. Notice that I'm not writing these as whole numbers. It's perfectly alright to leave these with the decimal values, even though I can't have 340.6 brown M&Ms. And this is just a theoretical value. So to finish this off, 0.16 times 2620 is, what am I getting? 419. 0.2 times 2620 is 524. 0.13 times 2620 is 340.6. And then lastly, 0.14 times 2620 is 366.8. Now, this chi-square test, if you look at some of the other slides that are on that handout, if these values are very different, chi-square, our test statistic, is going to be really big because we're expecting these numbers should be somewhat close to these. And if you look at some of these, the blue's certainly quite a bit off, but the rest of them aren't that bad. So, chi-square might not be too large. I don't know. I don't honestly remember what the results were. But so we've got our expected, we've got our observed. Now it's time to calculate chi-square. Now, chi-square is the sum, that's what that Greek letter means, of the observed value minus the expected value. Then we square that difference. Remember, that's the residual basically. We square the residuals, and then we're going to divide it by the expected. And what's the expected? Okay. And then once you find all those numbers, you find the sum of them. It works really well in a spreadsheet, and I'm sure I'll have an example on using a spreadsheet for this. I know I've done it with another course, at least another textbook. So let's calculate this chi-square statistic number. So remember, to calculate this statistic, we need to have the sum of the observed value minus the expected value. Then we have to square that residual divided by the expected value. And then once we find all those values, we're going to add them up. That'll be chi-square. So I decided to turn the table from rows into columns. And here's our observed values. Here's the expected values I just calculated. So the first step of the formula says subtract what you expect to get from what you observed. So I subtracted those and got negative 147.8. I subtracted those, got 30.4. I subtracted those, I got yada yada. Notice the only negative value is this one, and that's because this number is the only one that's larger than what we observed. Okay, the next step, we found all those residuals. That's this column. Now we're going to square each of those values. So I just 147.8 times 147.8 is that. 30.4 times 30.4 is that. Why isn't this negative, some of you might ask? Well, remember, when you square a negative, it turns positive. So I've got all those squared residuals are here. Now I'm going to divide each of those by what I expected. So this number divided by that expected number is that. And this number divided by that expected number is that, and so on and so forth. So this column represents all these numbers. Now if we add these all up, and that's what the chi-square statistic says to do, find the sum. When I did this earlier, I got 50.8-ish. And that's my chi-square number. So that's my test statistic. Well, what does that mean? The chi-square statistic, unlike the normal curve that we base the t distribution and the z distribution on, is a little bit different shape. And what matters is that its shape is this right-tailed, this skewed kind of distribution. And as your sample size gets larger and larger and larger, it flattens out and almost becomes more normal, to be honest with you. But it is a chi-square distribution. We always only care about the right tail. So these are always one-sided tests, right-tailed tests. And what depends on the shape is the degrees of freedom. And for the degrees of freedom for a goodness of fit model test, you just take a sample size and subtract 1, similar to what we've done in the past with standard deviation, that kind of thing. When we go to the a two-way table, contingency table, it's a little bit different calculation. I'll show you that. So the bigger the degrees of freedom, the more flattened out, and that depends on that gives you the idea what it is. So basically all we want to do is figure out what is that tail area, and that'll be the p-value, and we can decide whether that's really big or really small. If you look at this graph that I screen captured, remember our chi-square statistic was 50? Well, that's way out here off to the right. So I'm hoping you get a sense of that's a pretty extreme value. Not that area to the right is going to be pretty small. I'm thinking something might be up, that maybe this distribution and that they got out of that big case doesn't follow the expected distribution. In fact, that comes to mind. We have to set up HO and HA for this. So those of you that are not liking the symbolic ways of writing HO and HA are going to love this. So basically HO says, yep, these M&Ms follow what we expected them to find. And HA is you just say, hey, you can get more wordy, but why not just say HO is not true? Because it's either follows it or it does not. And then our test statistic is the chi-square value. The p-value, when I ran that on my calculator, to be honest with you, but it came up to be a very small number. So 0. And so we're going to reject HO. Looks like this case candy does not follow the expected distribution. Okay, and that's a goodness of fit test. Not too bad. Calculators work really well. You're going to put the observed, and she talks about that in the book, and there's plenty of YouTube videos about how to do it. So, and I did go find an applet to help you, and I got some screenshots of that. And here's the link on this PDF that you're going to have available of the Goodness Fit applet. I'll link that in the forum. Link that on the week 11 work. And when you're using this applet, it's kind of nice because you can use it depending on 2 different ways. Remember how we need to have the counts? Well, for this problem, they gave us the observed frequencies, which wasn't a problem, but they only gave us the expected proportions, what to get. We had to go through and calculate these by hand. What's great about this applet is you can put in your observed frequencies, what you expect to get, and then click calculate. And you see how it automatically filled in the expected counts? This is a bunch of extra stuff we don't need to worry about. But what you do want to pay attention to is, hey, there's our chi-square, there's degrees of freedom, and there's our p-value. It's telling us it's less than 1/10,000th, which is pretty close to 0. Okay, so that's one way to do this without a graphing calculator. It's really nice with a graphing calculator too. So the second kind of chi-square distribution we're going to look at, or chi-square test, or test of categorical variables, determines how can you tell, and this goes back to, it's related to what we did last week. How do you know if 2 quantitative variables have a fairly strong association? Well, you see if it's linear, you look at the graph, you see if it's linear. If it's not linear, you can look at R-squared, though we didn't get too much into that. But if the correlation is statistically significant, we can say there's some kind of predictive thing going on here. Not that there's a cause and effect thing, and the same thing here. We can't say there's a cause and effect. We can just say that there's some kind of association observed. And it works with categorical variables. So this came out of the textbook, I think, let's see. So it's about students in multiple grade schools. We ask what their personal goal is. Get good grades, be popular, be good in sports. And how important it was to having good looks were. So they said looks was 1 through 4. 1 least important. Oh, 1's very important. Least is 4 is least important. So how do you care how people look at you? And then what are your goals? And which time is there? As you see how this problem is asked, are these 2 sets of variables, 2 sets of categories, independent? Is there a relationship between whether or not somebody thinks looking good is important versus how they appear grades or sports or whatever? Okay, and so we're gonna test. They tell us to test it. So let's do this. Let's run through this. I mean, it's very similar to the goodness of fit test. It's just now instead of just one group of categories and one variable, we got four groups of categories as far as how you look, and three categories is how, depending on what's important to you. Now, another name for this is called a contingency table. I never use that word, but it is. It's another way, a two-way table, contingency table. These are the same words for the same thing. Notice this, what's nice about this example is they gave us the row totals, the table total, and they gave us the column total. So we're going to need that in order to calculate the observed values. I mean the expected values. Okay, so maybe I should start with HO and HA and actually do the test. So before we do the test, we should look at conditions, you know. Is my data counts? It sure as heck is. As long as we have randomization and the 10% condition. So you remember that's another thing that we don't want. I stole this out of another book. Don't worry about the 10% condition. Well, what it is your sample has to be, your population has to be 10 times bigger than your sample. Okay. We don't need to worry about that, folks. We do want to think about your expected counts have to be at least 5. If you've got a set of data where they aren't at least 5, you've got to combine them somehow. So maybe you'll have fewer categories, but you'll have the 5 met. Remember that. You're going to see this again. You're going to have to deal with this. At least 5 category. There's at least 5 in each cell. That's something that's going to come back if you don't catch that right now. Now, when I exported this sheet to this slideshow to PDF form, it didn't copy right. It's the same chi-square statistics, and this should be a sigma. This should be that Greek letter chi, but it's the same deal. Observed minus expected squared divided by the expected. But how we calculate the expected values is a little different because we've got a more complicated situation, more variables. Again, I'm not going to have you do this by hand. Maybe maybe I will. Not even MyOpen Math, you can use the applet for it. So I'm going to walk you through it once just so you see where they're coming from, because I think in this case it's good to know that. So let's show you how to get these expected counts. So the process of doing it this way is I'm looking for the expected count for somebody who felt looking good was number 1, and getting grades was number 1 for their goal. And to get that value, that should go right there. We're going to take the column total for that number 1. We're going to take the row total for the grades and multiply them, and then divide them by the table total. So to get that value, I'll do this. 1,885 times 247 divided by 478, and if I do that on my calculator, let's see, what do I get here? So 185 times 247. Be nice if I could type in 185. 185 times 247 divided by 478. I got 95.6. I'm going to do a little rounding, so I don't have to write so much. So 95.6. To get this next expected, I'm in column 2, notice. So I'm going to take the total for column 2. Notice I'm in row 1, so I'm going to take the row total for row 1 and multiply those. So I'm going to do 126 times 247 divided by 478. So 126 times 247 divided by 478. And if I'm doing this right, I got 65.1. So now how do I get this row here, this value here? hope you thought, oh, I'm going to take 101, multiply it by, because that's the sum of that column 3, I'm in column 3, times that row total, 247, divided by 478. So I'll write that one down one more time. So 108 times 247 divided by 478, 101, that should be. So 101 times 247 divided by 478. I got 52.1, 52.2. And then the last one, we're going to take 66 times 247 divided by 478. I'll let you fill that in. Actually, I'm going to have it all filled in here in a minute anyways. So how do we fill in this next row? Well, I'm still in column 1, but now I'm in row 2. So to get that value, I'm going to multiply. So to get this next row, we're going to do we're in column 1, but we want row 2. We're in the popular category, right? So we're going to do 185 times 141 divided by 478. So 185 times 141 divided by 478. And I'm getting 54.6 or thereabouts. To get this next number, we're going to do this. We're in column 2 and in row 2, so 126 times 141 divided by the column total. So 126 times 141 divided by the row total with 470, or table total of 478. So 126 times 126 times 141 divided by 478. I'm getting 37.2. And so on and so forth, right? We'll take 101 times 141 divided by 478, and 66 times 141 divided by 478. And for this last row, we're in column 1. We're going to take row 3, so 185 times 90 divided by 478 gives me this. So here are the observed values up here. Here's the expected value. Notice I don't have those totals. I shouldn't. Okay, so I've got 3 rows, 4 columns, 3 rows, 4 columns. Now to get the chi-square test, now that we've got everything we need, remember it's observed minus the expected. I'm going to have to square that difference, divide it by the expected, and then find the sum of all those numbers. So to get started here, I'm going to do 80. So I'm going to have grades, popular, sports, 1, 2, 3, 4. To get the first element here in that cell, that matrix is really where we're going. We're going to subtract 95.6 from 80. That gives me negative, what is that, 15.6. To get the next one, I'm going to take 66, subtract 65.1. I believe that's 0.9. To get the next one, I'm going to take 66 and subtract 52.2 from it. And get, let's see, what is that? That's going to be, let's see, it would be 13.8, I believe. Whoops. And then the last one would be 35 minus 34.1. That is 0.9. Notice all I'm doing right now, is getting the residuals. I'm just doing the subtraction part. To the next row, I'll do that for you. So 81 minus 54.6 is some number, and I don't know if I can do that in my head right now. So it would be 30, it would be, I'm going to cheat and use a calculator. Let's see here. So I'm taking 81 and I'm subtracting 54.6. 26.4. Then I'm going to do 30 minus, right? So I'm going to do 30 minus 37.2. Notice I'm matching it up cell by cell. Notice how this would probably work slick with a spreadsheet. So what is that? Negative 7.2. And so on and so forth. I won't bother filling the rest of this in, but you see where it's coming from. Next step would be to square each of those. Then divide each of them by the expected value. And then add them all up. So I decided to go to a spreadsheet and build this out on a spreadsheet. And just to walk you through my thinking, and you've already seen some of this, so to get the expected, this is the expected matrix. This is how many we expected to see. So I did 185 times 247 divided by 474. I got that number. I did 126 times 247 divided by 478, got that number, and so on and so forth. Then the next step is to subtract the observed and the expected. So I did observed minus expected, and I did that for each of these cells, came up with that. Then I squared each of those differences. So I took negative 15.59, whatever, and squared it, got that. Notice that's raising to the second power, not taking the square root, okay? People get confused with that sometimes. So that's the square. Now the next step in the chi-square test statistic is divide each of these squared differences by the expected. So this number got divided by that number, and that's what the result was. I did this number divided by this number, got that. Did that for all 12 cells. Then I added them up, and that's my test statistic, the 36.69669. Now we need some way of finding a p-value for that, and it's the same distribution as what we just dealt with. You have to know the degrees of freedom. Now, for this, in one of those earlier slides I had, the degrees of freedom when you're dealing with this kind of test is a little different than n-1. What you're going to do is you're going to take the number of rows and subtract 1. Take the number of columns and subtract 1. And then multiply those two answers. So for this one, I've got 3 rows, so 3 minus 1 is 2. I've got 4 columns, so 4 minus 1 is 3. So 3 times 2 is 6 degrees of freedom. Now, if we had to use a table, or if like Applet we were using, and there's many out there that have you do that, they're looking for the test statistic. They're looking for the 36.696 is our chi-square test. They're going to be looking for the degrees of freedom. They'll tell you the p-value. You're going to use the one, if you use the Applet I'm going to show you in a minute, you don't need to do that. I'll have this link for this applet available in the works work, and then all you have to do to use this applet is to type in your observed values, and notice I did it just like the table. It's a matrix basically, and then you click calculate. It gives you chi-square, it gives you the degrees of freedom, it gives you the p-value. So HO was these are independent. That how your appearance should be, how you care about how your appearance is perceived, is that independent from these other goals, whether you're popular or like good grades. And because of this p-value, very small p-value, we're going to reject our HO. It looks like these are not independent. It looks like there's some kind of association going on between how your appearance is and what your goals are. Okay, and we don't know what they are. I mean, maybe we could look at the differences a little closer to tell. We don't want to read too much into this because we really don't know. Without further study, we don't really know what's what's going on. But we know there is something, we know they're not independent. There is something going on here. So those are the two things we're going to look at. There is another chi-square test we can use. This book doesn't deal with it, and honestly, it's the same kind of idea. We don't need to do that. If you ever have to take stats 2, you'll look at it real closely. Okay, so I guess that's it. You should look at the other, you could thumb through the booklet, the book. You can look at those other slides I'm going to provide you. But that is it in a nutshell.